Look at these numbers. Some decimals stop like 0.25 and some repeat a pattern like 0.3333. And then there are the ones that never stop and never repeat like 0.101001, so on, square root of 2, and pi. What's so different about these numbers? Today we'll finally make sense of why some numbers behave so nicely while others go on forever with no pattern. Hi everyone, welcome back to Teaching Math. This video will make learning rational and irrational numbers simple. By the end, you will be able to tell if the number is rational or irrational and recognize when the decimal terminates, repeats, or never repeats. And then also you're going to be able to show how these type of numbers fit on a real number line. Let's get started. Well, every number you've ever worked with actually belongs to a big family called the real number system, and it's organized like layers. Let's start with natural numbers. The ones you first learned when you started counting, like 1, 2, 3, 4, 5, and so on. These are often called counting numbers because we use them to count things that exist, like 3 apples or 5 pencils. Next, we add 0 to that list. When we include 0, we now have the whole numbers, 0, 1, 2, 3, and so on. This new group helps us describe situations when there's nothing, like having $0 left. But what if we owe money? That's where integers come in. Integers include all the whole numbers and their opposites, like -2, -1, 0, 1, 2. And we use these numbers to talk about a loss, a temperature below 0, directions, things that go both positive and negative. Now, sometimes we need numbers in between integers like half, -3/4, or 0.25 when we are cutting pizza or measuring something. These are rational numbers. They can always be written as fractions, like one integer divided by another, given that the denominator is not a 0. Their decimals either terminate, that means stop, like 0.25, or repeat, like 0.3333. But remember, when the decimals repeat, they repeat in a pattern fashion. 0.33 is a pattern. It keeps on going and being 3 and 3 and 3. And 0.323232 shows a pattern as well. But here's where it gets interesting. Not all decimals can be written as nice, neat fractions. Some go on forever without any pattern, like square root of 2 equals 1.41421356, and so on. It goes on forever. Or pi, we know it goes on forever, and it equals to 3.1415926, and so on. These are irrational numbers. We still use them because they're real values, and we use them in geometry or measurements, but they can't be written as a ratio of 2 integers, meaning they cannot be fractions. When we put both rational and irrational numbers together, we get the entire set of real numbers. Real numbers are everything that can be shown on a number line. Every fraction, every decimal, every square root, every pi you can imagine. Now that we know where rational numbers fit in a big family of real numbers, let's take a closer look at what makes them special. A rational number is any number that can be written as a fraction. That's one integer divided by another, as long as the denominator isn't 0. In here, we can see A divide by B, and then B cannot be 0. So, for example, half equals 0.5. As you can see, we have the fraction and decimal version of the same number, and this is a rational number. 3/4 is the same thing, as well as 1/3, which is non-terminating decimal, which we can rewrite also as 0.3 and a bar notation on top. If there were two numbers repeating, we would have written 0.343434 three times and 1, 2, 3 dots, or 0.34 bar notation on top of both numbers. Here you're going to ask me, well, what happens to whole numbers? Are they rational numbers? Yes, of course they are rational numbers because every single whole number can be written as a fraction. For instance, 4 can be written 4/1 because when we divide 4 by 1, it will still equal 4. And if we say -5, we can still rewrite this as -5 divided by 1. The key idea to remember here is this: if you can write it as a fraction, it is a rational number. And when you write a rational number as a decimal, it will always either end clearly like 0.5, or it will repeat in a pattern way, like over here, 0.333 or 0.343434. All right, let's go a little bit deeper and see what rational decimals actually look like. There are two types, as we discussed before, of rational decimals: terminating or repeating. A terminating decimal is one that ends. For example, 1/4 is 0.25. 3/5 is 0.6. As you can see, the number ends at 6, and in here at the top, the number ends at 5. Now, repeating decimal is one that keeps on going forever, but in a pattern. For instance, 1/6 equals 0.16666. As you can see, 6 will repeat forever, and it's a pattern. 7/9 is 0.7777. The important thing is to note that even though they go on forever, they do follow a rule. The pattern repeats. That means we can still write them as a fraction, which is why they're still rational numbers. Here's a quick challenge. If you see a decimal that goes on forever but repeats something like 0.272727, it's repeating, not random. That's what makes it rational. Let's talk about irrational numbers. Irrational numbers are the rebels of the number world. You can't write them as fractions no matter how hard you try. They just don't fit that A divided by B pattern. Their decimals never end and never repeat. That means there's no pattern, no cycle, no way to predict the next digit. Let's take a look at a few famous examples. Square root of 2 is 1.41421356. Pi, we are very familiar with pi, equals 3.14159265, and square root of 5 is 2.2360679. I want you to notice something about our square root of 2 and 5. Those are not perfect squares. And remember, perfect square is a result of a number multiplied by itself. For instance, 3 times 3 equals 9. 4 times 4 equals 16. And there isn't any number for square root of 5 that could be multiplied by itself to equal 5. So therefore, those are irrational numbers. So you can think of irrational numbers as the ones that fill in the gaps on the number line. They are not fractions, but they are still real numbers. Here's a visual example for you. Here's a square that has side length of 1 unit. The diagonal of this square is square root of 2. It is a real distance, but you can't write it neatly as a fraction. So we estimate the measurement. So remember this phrase, irrational numbers equal non-terminating and non-repeating decimals. So how do we handle these never-ending decimals if we can't write them as fractions? We estimate them, as I mentioned earlier. Here's a trick. You find the two perfect squares that your number sits between. For example, square root of 2 sits between 1 square, which equals 1, and 2 square, which equals 4. Since 2 is closer to 1 than to 4, square root of 2 is about 1.414. Similarly, square root of 50 is between 7 squared, which is 49, and 8 squared, which is 64. That means 50 squared is a little more than 7, so we estimate it's about 707. All right, let's take a look at another example, square root of 20. We wrote down with a calculator that it equals 4.472 between 4 squared and 5 squared. So how do we determine this? Here it is. We have 4 squared, which equals 16, and we have 5 squared, which equals 25. Well, 20 is in between 16 and 25. As you notice, it's really in between. It's neither close to 16 nor to 25. It's almost in an equal distance. Therefore, as you can see, the number is 4.425. So here you could have estimated 4.5. The idea here is that even though irrational numbers go on forever, we can still get really close to their value, close enough to use them in real-world situations like geometry or measurements. I have created another video that explains how to get very close estimate of square root of any number, including irrational numbers. So please watch that video if you want more details about how to estimate to very close numbers. Now let's put rational and irrational numbers side by side to make the differences crystal clear. Rational numbers can be written as fractions. They're decimal and or repeat, and they follow a predictable rule. That means there is a pattern. Here's an example: half, -3, 0.25, and 3.333. Can we find this on the number line? The answer is yes. Irrational numbers cannot be fractions. No. And they can have a decimal form, but it never ends and never repeats. The trick here is it does not have a pattern. For example, square root of 2, pi, square root of 3, square root of 5, square root of 17, and so on. Can we find this on the number line? The absolute answer is yes. Let's bring it all together. On a real number line, you will find integers like -5, 4, or 0. You will also find rational numbers like half and -1.5. And you will also find square root of 2, which is approximately 1.41, pi, which will be 3.14, and negative square root of 3, which is approximately -1.73. Every single one of these numbers fits perfectly somewhere on the line. And as you can see, irrational numbers are approximation where it will fit. The line never ends and it doesn't skip. There's always another number between any 2 points, whether it's rational or irrational. That's the beauty of real number systems. It continues. It fits every space between numbers. All right, now it's your turn. Test your learning and your knowledge. Pause the video here and then come back with your answers. So let's first start the first one. Question A, the answer is B and E. It's asking you which is an irrational number. We already talked about square root of 2, and this is not a perfect square, therefore it's an irrational number. And E, because the decimals are non-terminating, we know that. And also it's non-repeating because it doesn't show any pattern. Second question, between which two integers does 40 lie? And let's take a look. All right, 40 lies between 6 and 7. 6 squared equals 36 and 7 squared equals 49. So 40 is closer to 6 than 7. So the answer could be possibly 6.3 or 4. So the actual answer on the calculator is 6.324, etc. And we can use 6.32 or 6.3 as our estimated number. All right, let's recap. We made it all the way to the end, and we're ready for a recap. We learned that rational numbers are fractions, have terminating and repeating decimals, and they show up as, if it's non-terminating decimals, they show up as a pattern. Irrational numbers are decimals that never terminate or repeat, and they do not have a pattern, and they cannot be written as fractions. Both can be placed on the number line. You can approximate irrational numbers like square root of 5, square root of 2, or pi. You also learn how to estimate irrational numbers by comparing them to perfect squares, which is a big part of our Common Core standards. Awesome job. Pat on your back. You now understand what real numbers are and how rational and irrational numbers fit together. You can look at any decimal or square root and know exactly which category it belongs to. It's powerful. In our next lesson, we'll dive deeper in terminating and non-terminating decimal and how to recognize square and cube roots in real-world problems. Don't forget to like and subscribe and comment which number surprised you the most. And if you want more practice, download the worksheet linked below. Great work today. And remember, learning math takes practice, patience, and perseverance. See you next time.